Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper data structures. In this module, we will be talking about graph ADT and graph traversals. Now, if you look at graph, we have looked at an introduction to graphs and certain terminologies associated with the graph in the last module. Graph traversals also we have seen, but we have seen graph traversal as an application of stacks and queues. So, stacks the application was depth first search and breadth first search the application was queues. So, but in this we are looking at it from the graph viewpoint, we will see some properties where it is used and so on. So, that is what we are going to do in this module. So, these are the people responsible for the creation of this module, and the learning objectives of this module are as follows: to describe the graph ADT. So, just like we had described list ADT, stack ADT, queue ADT and so on, here a tree ADT, we are going to describe the graph ADT. As we have always spoken, a graph ADT means we are talking about a graph along with some operations, and what operations you have to include in each graph ADT depends on the applications for which the graph is going to be used. And then we are going to discuss the operations associated with graphs, what are the typical operations associated with graphs, and then we are going to explain in detail the breadth first search and the depth first search. The keywords that you are going to use here are paths and traversals. Now, what are graphs ADTs? So, two options are there for defining graphs, one in which vertices contain values and the other in which vertices do not contain values. So, these are some typical options for representing graphs. Graphs is really versatile in the sense that how you represent it. The operations of an ADT graph, typical operations are create an empty graph. For any abstract data type or any data structure, this is a typical operation. Determine whether the graph is empty, determine the number of vertices in a graph, determine the number of edges in a graph. So, these two are specific to graph, the other two are general any ADT. Then let us take an example. The graphs are a formalism for representing relationship between entities. So, a graph G is represented by G is equal to V comma E. B is the number of vertices, the set of vertices, and E is the set of edges. And here we have V is 3 vertices, Ram, Lakshmi and Hari. We had seen the same example in the previous module also. And the edges here are, there is an edge between Hari and Lakshmi. This is a directed edge, and then you have a vertex between Ram and Lakshmi, and we have one between Lakshmi and Ram. As you already know, graphs can be directed, undirected, can be weighted, unweighted. And the operations here include iterating over the vertices, that is going one after the other in the vertices, iterating over edges, they are not the same, iterating over vertices adjacent to a specific vertex, asking whether an edge exists which connecting two vertices. So, now slightly we are going into differences, just iterating over the vertices. Iterating means going over all the vertices, going over all the edges, iterating over the vertices that are adjacent to a specific vertex. So, who are the neighbors, and then asking whether an edge exists between any two vertices. So, these are some of the operations that a graph ADT can have. So, we will just again go through the what there can be. So, ADT graph operations, first test whether the graph is empty, get the number of vertices in a graph, get the number of edges in a graph, see whether an edge exists between two given vertices. For weighted graphs, you will have to return the weight value, depends on whether the graph ADT you define is a weighted graph or not. If it is not a weighted graph, you will just say okay, the edge exists or not. If it is a weighted graph, you will also output the weight associated with that particular edge. Then insert a vertex in a graph whose vertices have distinct values that differ from the new vertices value. So, you want to insert a vertex in the graph, and that graph has vertices that have distinct values from the new one. So, you want to insert, that is another next one. Then insert an edge between two given vertices in a graph. So, inserting a vertex does not necessarily, you do not have to insert an edge, or given any graph you can insert a new edge between given two vertices. Then if you want to remove a specified vertex, this is special because when you remove a vertex from a graph, you also have to remove any edges between that vertex and other vertices. So, removal is not just removing of a vertex, you have to also remove all the associated edges of that particular vertex. And then you can just remove an edge between any two vertices in a graph, that is allowed. Insertion, similarly edge here does not mean anything else, the vertices can still be there. And then retrieve from graph vertex that contains a given value. So, you want to retrieve a vertex that contains a particular value, that also can be done. So, example of a graph ADT. So, there are some data elements For example, vertices and edges. Every graph will have vertices and edges. Operations get degree u returns a degree of vertex u. If it is out degree, I mean if you have a directed graph, then you have out degree. Otherwise, it just if it is an undirected graph, this again in any graph ADT you have to describe whether the graph ADT you are defining is a directed or undirected, weighted or unweighted. So, here we are generally saying, so it returns a degree of a vertex u if it is undirected. If it is directed, we are talking when you say degree, it means out degree. Get adjacent u means returns a list of vertices adjacent to the vertex u, and if it is a directed graph, it is a list of vertices that u points to. So, it is a list of vertices that u points to. There it gives a number, here it gives the actual vertices. Is adjacent to u comma v returns true if vertex is adjacent to vertex u and false otherwise. So, there are some associated algorithms for finding this also. An important operation of a graph is a traversal. So, given a graph G equal to V comma E, where again we have already spoken, vertex V find which belongs to a set V and an edge which connects V. Then you have a depth first search or DFS. It is also something like a pre-order traversal which we have seen in trees. We have also seen depth first search itself when we are talking about an application of application. Then we have breadth first search which is a level order traversal. Okay. And then there are something called path problems. We will define this as we go along in the modules on graph. Then we have connectedness problems and then spanning tree problems. So, see some of these are typical graph operations, of which path finding is a very important operation, especially in the weighted graph. In this example is a weighted undirected graph. Now, we are asked to find the path between 1 and 8, let us assume. Then this is a path between 1 and 8 and the length of the path is 20. Now, suppose this is not the only path between 1 and 8. So, you can have another path also. So, that path is 1 to 4, 4 to 6, 6 to 7, 7 to 5, 5 to 9 and 9 to 8. So, this is another path. So, the path length is 28. So, here we have two paths. So, finding a path between any two vertices is an important problem. The applications of graphs are so varied that all these operations find particular applications. We will come to that as we go along. So, here we have two paths between 1 and 8, one with a path length of 20 and 2 with a path length of 28. These weights that we have there could be the cost of travel or could be the distance, it could be anything. It depends on what your application is. Now, the next topic we are going to discuss is connected graph and connected components. So, when in an undirected graph, there is a path between every pair of vertices, then it is called a connected component. So, a maximal subgraph that is connected means you cannot add vertices and edges from the original graph and retain, you cannot add vertices and edges from the original graph and retain the connectedness of this component. A connected graph has exactly one component. If it is a completely connected graph, it will have one component only. This example here has got two components. You cannot add anything without and still retain the connectedness. That is the meaning of this. Now, this is a connected graph and connected components. This is very important later on when we discuss some applications. Now, a typical application could be communication network problems. Is the network connected? That means can we communicate between every pair of cities? For this you have to find the components and we want to construct smallest number of feasible links so that the resulting network is connected. So, what we want to do, when we have a set of cities and we want to have links between the cities so that they all become connected. Now, our problem here is to find the smallest number of feasible links that you need to make the resulting network connected. This is a typical problem in the communication network. There are other important and some interesting problems. One is what is called technically as Hamilton circuit. This is a path that begins at a vertex V, passes through every vertex in the graph exactly once and terminates at V. This is called a Hamilton circuit. This also has its application. Then you have the famous travelling salesman problem. This is again a graph problem. So, it is a variation of the Hamilton circuit, except in the Hamilton circuit you had no weights or anything. In the travelling salesman problem you have a weight associated. It is a weighted graph and it represents a road map supposed to So, the circuit that you take or the path that you take should be the least expensive. So, that is the travelling salesman problem. Then you have circuit. A circuit is a type of cycle that visits each vertex or each edge exactly once, no more than once. And then an Euler circuit is a special case of circuit where it begins as a specified vertex, there it visits each vertex. Here you start at specified vertex, pass through each edge exactly once and ends at the same specified vertex. So, that is an Euler circuit. It only exists if every vertex has an even number of edges, otherwise you cannot form the Euler circuit. There are some other interesting problem associated. One is the 3 utilities problem, where we try to find how we can give the best 3 utilities for a number of households that are connected. Remember, all these needs connection lines, for example, telephone, the water connection and the network connection, TV connection. Another interesting problem is a planar graph. What this says is, can we draw a line in a plane in at least one way so that no 2 edges cross. So, this is another problem that is typically a mathematical problem also. Graph is a very important mathematical structure also. Then you have the famous 4 color problem. Given a planar graph, can you color the vertices so that no adjacent edges have the same color, and you are given 4 colors. You can start, normally they talk about as 4 colors. So, given a planar graph, can you color the vertices so that 2 adjacent vertices have the same color, but you are given only 4 colors, that is a constraint. So, we will go and look a little more detail into graph searching problems. In this module, we are only going to look at the general graph searching problems, algorithms, and we are going to look at the comparison between the two basically. So, what is the graph searching problem? Searching a graph is systematically follow the edges of a graph to visit the vertices in the graph. So, it is used to discover the structure of a graph. So, there are standard graph searching algorithms as already discussed. One is the breadth first search and the other is the depth first search. Depth first search is the pre-order traversal and breadth first search is the level by level traversal. Now, let us take the breadth first search. Now, the breadth first search, it visits every vertex adjacent to a vertex V that it can before visiting any other vertex. So, it tries to the breadth first search visits every vertex adjacent to a vertex V. A is first visited, first visited, first explored strategy. It uses a first visited, first explored. So, whichever node you have first visited, that is the node that is first explored before you go to the next node. It is a recursive form is possible to do the breadth first search. Methodology means it expands the frontier between discovered and undiscovered vertices uniformly across the breadth of the frontier. So, what we are trying to say is it takes a node which has been first seen, explores that before going to the second node and exploring that. So, a vertex is discovered the first time it is encountered during the search, and a vertex is finished if all vertices adjacent to that particular vertex has been discovered. So, again we will repeat, a vertex is discovered the first time you encountered it during a search, and vertex is finished if all the vertices adjacent to this has also been discovered. So, that is the methodology that is generally followed. So, follows the following rules. So, you first select an unvisited node X, okay, have it to be a root in a BFS tree if it is a tree, and its level is called the current level. From each node Z in the current level, in the order in which the level of the nodes were visit all the unvisited neighbors or adjacent to neighbors of Z. The newly visited nodes from this level form the new level that becomes the next current level. Repeat step 2 until no more nodes can be visited. If there are still unvisited nodes, you go back to step 1 and continue the process. So, this is what is breadth first search. What are you doing? You are selecting a vertex, finding all its neighbors, the current level, and visit all the unvisited neighbors of set. Okay. The newly visited nodes from this level form a new level, and that will be again visited, its neighbors will be visited and so on. So, analysis of, we will take an example later. So, the analysis of breadth first is initialization of the whole thing takes order of V. Remember, V is the number of vertices. It is a traversal loop. After initialization, each vertex is enqueued and dequeued at most once, and each operation takes of the order of 1. So, total time for queuing is of the order of V. The adjacency list of each vertex is scanned at most once. So, the sum of the length of all adjacency lists put together is obviously the number of edges it has, which is of the order of E. So, summing up everything, the total running time of a breadth first search is of the order of V plus E. It is the linear in the size of the adjacency list representation of a graph. Remember, a graph could be represented as adjacency list or adjacency matrix. Here he is talking about the adjacency list representation. Now, the key BFS tree property is that every root leaf path in a BF has the fewest number of edges possible. So, that is the property of a BFS. By nature of definition, it has the fewest. Okay. So, that is the idea, because you will not take any from the root to the leaf, you will go as far as possible, you will go and find that path which has the least number of edges. So, application using the template method pattern, we can specialize the BFS traversal of a graph G to solve the following problems in the order of n plus m time. Compute the connected components of G. Remember what are connected components? Compute a spanning forest. We will go into detail about this in the next two modules. Find a simple cycle in G or report that G is a forest. If it does not have a cycle, then it is a forest. Given two vertices of G, find a path in G between them with a minimum number of edges or report that no such path exists. So, this is the some of the operations that you can do or applications that you can, the operations you can use for the applications. So, next we have DFS versus BFS, that is depth first search versus breadth first search. So, these are some applications which we will see in detail: spanning forest, connected components, path cycles, DFS and BFS can be used. We have discussed only BFS. Shortest paths, BFS is the best. By connected components, DFS is the best. So, if you look at BFS, BFS, you will see that you start at level 0, then do everything at level 1, then go to level 2, that is BFS. Depth first is the other way around, we will come into detail about this later. Now, if you look at back edge VW, W is an ancestor of V in the tree of discovery edges. Why are we talking about this? We will come to that later. W is, what is a back edge? V and W. W is an ancestor of V in the tree of discovery edges. So, it is an ancestor, it is visited before V. So, that is a back edge. Cross edge is W is in this, that is defined for DFS. In BFS, W is in the same level as V or in the next level in the tree of discovery edges. So, both these back edge and cross edge are discussed in terms of the traversal or discovery order. So, ancestor in the discovery is the back edge and cross edge is level based on BFS. So, let us go to depth first search now more in detail. The depth first search traversal proceeds along a path from V as deeply into the graph as possible before you back up. Does not completely specify the order in which it should visit the vertices adjacent to V. Last visited, first explored. So, in the previous case what happened in the breadth first, whatever we visited first was explored first, that is why it used a Q data structure. In the depth first search, a last visited is first explored. So, it uses a last in first out of the stack. It is an iterative algorithm using a stack. So, DFS follows the following rules: select an unvisited node X, visit it and treat it as a current node. Find an unvisited neighbor of the current node, visit it and make it the new current node. If the current node has no unvisited neighbors, backtrack to its parent, make the parent the new current node. Repeat steps 3 and 4 until no more nodes are visited. If there are still unvisited nodes, repeat up to step 1. So, this is the depth first search. What are you doing? You are taking a node, okay, visiting it and then treat it as a current node. Then find an unvisited neighbor of this current node, visit it, make it the new current node and keep doing this. So, what you are doing is you are the last visited node is the one which is next explored. Okay. So, the explore edges out of the most recently discovered vertex V. When all edges of V have been explored, backtrack to explore other edges, leaving the vertex from which V has just come. It was discovered, its predecessor. So, search as deep as possible first, that is a strategy of the DFS, and continue until all vertices reachable from the original source is discovered. If any undiscovered vertices remain, then one of them is chosen as a new source and the search is repeated from that source. So, analysis, process each node, so of the order of V plus the total cost of executing the DFS visit. This is approximately of the order of E. So, the total running time of both the BFS and the DFS is of the order of V plus E. Now, let us take an example of a traversal. So, let us take breadth first, the same graph we are going to consider. So, let us say we are starting from A. So, you have to visit all the neighbors of A. So, that is 1, this is the order of the traversal. So, then I am just taking it as in the in the alphabetic order. Normally that is what is done. So, you will see that these 3 are the neighbors of A. So, you have 2, 3 and 4 shown red here. Next what we have to do is, remember the first one seen is the first one explored. So, next is B. So, I take B and I have to find all neighbors of B which has not yet been visited. So, the neighbors of B are C, F and G, but F has already been visited from A. So, what is left behind is C and G. So, C and G are the next ones that are traversed. So, I have C and G. Next I have finished CG. Now, the next I have to take is F. So, from F the neighbors of F are D and H. Of course, G, C all are neighbors, but those are already been visited. Remember, everywhere it is not yet visited. So, D and H are the next ones. So, that is visited, and then finally 7, 8 and then E is visited. So, that is 9. So, this is the visiting order. Of course, after I find A, BF I could have done IFB, still a depth first, I mean breadth first only, but normally if we follow the lexicographic order, no, nothing great, I mean nothing, it is a policy that is followed, that is all. So, you have A, BFI, then that is A's neighbors BFI, breadth first, then B's neighbor, so B's neighbor the first one that is visited, CG. F is also all neighbors that has not yet been visited, that is CG. After that F's neighbor, then like that. So, this is the breadth first search. Now, let us take the same graph. Depth first, what you do? You visit A first, okay. Then take A's child B. Now, you do B's child next. So, that is C. Then C's child, okay. So, C's child is next. So, that is D. Then D's child E. E's child F. I could have taken H also, I have taken F. Then F's child G, G's child that, and then whatever has not been visited. After this H does not have a direct relationship to I, but I is an unvisited node which has been, so that has to be considered A's neighbor. So, this is the breadth first and the depth first with an example. Now, DFS introduced an important distinction among edges in the original graph, which we already slightly spoke about. So, tree edge is an encounter new vertex, back edge is from the descendant to the ancestor, forward edge is from ancestor to descendant, and cross edge is between a tree or subtrees. Trees and back edges are important. Most algorithms do not distinguish between forward and cross. Then the classification is like this: in the depth first forest found by exploring UV, back edge is where U is a descendant of V in the depth first search. So, it is defined in depth first search only. Forward is where V is a descendant of U, but not a tree edge, and cross edge is any other edge, can go between vertices in the same depth first tree or in the depth first trees. Now, so for example, here you have tree edges and then you have the back edges marked by red, blue, then forward edges. So, from D to the 1 to 5 is a forward edge, 14 and then tree edges are there, and you have the cross edges. Now, we can specialize the DFS algorithm to find a path between any two given vertices U and Z using the template method pattern. We can call DFS G comma U with U as the start vertex if you want. We can use a stack S to keep track of the path between the start vertex and the current vertex, so that you get the path of vertices also. As soon as the destination vertex S Z is encountered, we return the path as the contents of the stack. So, this is a very easy implementation for path finding. So, it just follows the DFS algorithm, except that you start with U as the vertex, and then in the middle of the DFS algorithm, if you reach the destination specified Z, then you stop. So, that is the path finding algorithm. Then you have cycle finding algorithm. We can specialize the DFS algorithm again to find a simple cycle using again the template method pattern. We use a stack S. This is just a method that you can use, which is basically a DFS. So, we use a stack S to keep track of the path between the start vertex and the current vertex. As soon as a back edge means you already you have encountered that is encountered, we return the cycle as a portion of the stack from the top to the vertex where W. So, that is the vertex. When you are keeping on doing the depth first search, you encounter a stack vertex W, okay, and then you keep going and then after some point again you encounter W. So, every time you put some vertex into the stack, you have to look whether it is there in W, I mean it is there, and then when you see this W up to, from this W up to the top, whatever you output will be the cycle. So, in this particular algorithm we have described the graph ADT, we have discussed the operations associated with graph, and we have explained in detail the breadth first search and the depth first search. In this we did not look at how a stack or a queue was used to do the depth first or breadth first search, but we looked at how the depth first searches can be modified in order to find paths, in order to find cycles, what are the different edges defined, what is a BFS, how is a BFS different from a DFS, and such type of issues what we discussed in this module. So, thank you.